Now we solve some problems with undetermined coefficient methods. Find a particular solution of fourth derivative of y plus 2 times y double prime plus y is equal to 3 sin x minus 5 cos x. To find the general solution of the homogeneous equation, we look at the auxiliary equation, which is fourth power of m plus 2m square plus 1 is equal to 0. We factorize, we get m square plus 1 whole square equal to 0. So from this, we can find a basis for the solution space, which is also the basis for the kernel L, where L is the differential operator corresponding to this non-homogeneous differential equation. So the basis for the kernel L, or the basis for the solution space, is cos x, sin x cos x sin x. Clearly, here iota is a root of this equation, and it is with multiplicity 2. Therefore, we have multiplied x with cos x and sin x. So the candidate for particular solution, by using the scheme that I have described earlier for particular solution of a undetermined coefficient method, is y is equal to x square bracket a cos x plus b sin x. Here sin x and cos x are solutions of the homogeneous equation, and they correspond to the root iota of the auxiliary equation, and iota already appears as a root of the auxiliary equation with multiplicity 2. So it should be x raised to mu iota, which is x raised to 2, because mu iota is 2, and then bracket, and we have from this sin x and cos x in Rx, we know that here we should multiply x square by a cos x plus b sin x. So we substitute this candidate for particular solution in the non-homogeneous differential equation. Then we get this. We collect the coefficient of cos x and equate it to 0. We collect the coefficient of sin x and equate it to 0. This gives us value of a and b. That value we put here to obtain the particular solution of this non-homogeneous ODE. So the final solution is yx is equal to x square bracket 5 by 8 cos x minus 3 by 8 sin x. Here is another example. Find the candidate solution for fourth derivative of y minus third derivative of y minus y double prime plus y prime is equal to x square plus 4 plus x sin x. The auxiliary or the characteristic equation is m raised to 4 minus m cube minus m square plus 1, which can be factorized as m times m minus 1 whole square times bracket m plus 1 bracket close is equal to 0. So from this we can see what are the roots of the characteristic equation, and so the solution of the homogeneous differential equation can be obtained, and we can find a basis of the solution of the homogeneous equation, which is also a basis of the kernel L. So a basis is 1 comma e raised to x comma x e raised to x comma e raised to minus x. Here 1 is the root of the characteristic equation with multiplicity 2. So we have ex and xex. So what is the form of the candidate solution? So here the Rx can be written as R1x plus R2x, where R1x is x square plus 4. Looking at x square plus 4, we can formalize the candidate solution for this part to be ax square plus bx plus c, where a, b, c are undetermined coefficient. We have to find those coefficients by substituting into the differential equation. Now, whether we need to modify this depending on the multiplicity of this root. So here, this is a polynomial, that means it corresponds to the root 0 of the characteristic equation, because we can write this as x square plus 4 times e raised to 0x, and 0 occurs as a root of the characteristic equation with multiplicity 1. So we have to multiply this with x raised to mu 0, which is x raised to 1. So we modify this and write it as x times bracket ax square plus bx plus c. This is the candidate for particular solution, which is suggested by this part, x square plus 4. Now we look at R2, that is x sin x, and this suggests us that the candidate solution should be q1x cos x plus q2x sin x, where q1 and q2 are of the degree 1, because here it is of the form x sin x, where x power is 1. So the degree of q1 and q2 should be 1 here. Q1 Q2, I am referring to the scheme that I described in previous lectures. Now, whether we need to modify this solution, we don't need to modify this solution, because sin x and cos x are not solution of the homogeneous equation. So our finite candidate solution, or final candidate solution, is the sum of this and this. So it is x bracket x square plus bx plus c bracket close plus bracket alpha x plus beta bracket close cos x plus bracket gamma x plus delta bracket close sin x. The next problem is find the candidate solution for fourth derivative of y minus 2 times double derivative of y plus y is equal to x square e raised to x plus e raised to 2x. Here the auxiliary equation is m raised to 4 minus 2m square plus 1 equal to 0. So we can factorize it as m minus 1 whole square times m plus 1 whole square equal to 0. From this, the basis of the kernel L is e raised to x, x e raised to x, e raised to minus x, and x e raised to minus x, because both 1 and minus 1 occur as a root of the auxiliary equation with multiplicity 2. Therefore, we have multiplied by x e raised to x also and e raised to minus x also. Now looking at the Rx, we write Rx as R1x plus R2x. Now here R2x is e raised to 2x. That suggests that our candidate solution for that part should be a e raised to 2x. Do we need modification for this? No, because 2 is not a root of the auxiliary equation. The other part, R1x, which is equal to x square e raised to x, that suggests that the candidate for the particular solution for that part should be qx e raised to x, where qx is of degree 2, because here x is with power 2. So we have bx square plus cx plus d, this whole thing multiplied to ex, where b, c and d has to be determined by substituting into the differential equation. Now does this need to be modified? For that we have to check whether 1 is a root of the auxiliary equation. Yes, 1 is a root of the auxiliary equation with multiplicity 2. So we have to multiply this by x raised to mu1. mu1 is 2, the multiplicity is 2, so you have to multiply this with x square. So the candidate for particular solution corresponding to R1x is x square times bracket b plus x square plus cx plus d bracket close e raised to x. So the final candidate for the particular solution is the sum of this and this, that is a e raised to 2x plus x square into bracket bx square plus cx plus d bracket close e raised to x. Here are some review questions. For a non-homogeneous equation y double prime minus 5y prime plus 6y equal to x cos x, the form of particular solution yp using method of undetermined coefficient is dash. Here are 4 options. You can pause the video and find out the solution. Here one observes that x cos x is not a solution of the homogeneous differential equation. So we don't need to modify the particular solution which is suggested by the Rx. From Rx, the particular solution that is suggested is q1 cos x plus q2 sin x, where both q1 and q2 are of degree 1. So it should be the option B, that is bracket a0 plus a1x bracket close cos x plus bracket b0 plus b1x sin x. The review question 2 is solve initial value problem y double prime plus bracket 1 plus 1 by y bracket close y prime square is equal to 0 with initial condition y naught equal to 1 and y prime 0 is equal to 1 by a. Note that this is a second order differential equation, but to solve this second order differential equation we can use a trick. We can convert it into a first order differential equation and solve it. You can pause the video and try to solve the question on your own. So here the form of differential equation suggests that we can take the dependent variable to be v, where v is equal to y prime. So y double prime is equal to dv by dx, which is equal to dy by dx times dv by dy, which is equal to v times dv by dy, because dy by dx is v from here. So we can substitute this in the given initial value problem, and then the initial value problem becomes a first order differential equation in the dependent variable v. So this y double prime is replaced by v dv by dy. Then we have that plus bracket 1 plus 1 by y bracket, and thus y prime becomes v. So you have v square equal to 0. Now this is in form of separable ODE. So we can rearrange the terms. We can bring this v square in the denominator here. So we have dv by v, and we can take this dy on the other side, and then we can integrate to get the solution. So here dv by v appears after rearrangement. So that term will give on integration log mod v, and here integration of this term will give you y, and integration of this term with dy will give log mod y, and there will be some constant. So from that we get the solution Vy is equal to c times e raised to minus y raised to minus 1. Now we can substitute the initial condition here. See, we know that when x is equal to 0, y is equal to 1. And when x is equal to 0, y prime is 1 by a. So in other words, we can say when y is equal to 1, y prime is equal to 1 by a. So we substitute y is equal to 1, then v should be equal to 1 by a. So here 1 by a is equal to c times e raised to minus 1 times 1. So here Vy is equal to 1 by e, and here e raised to minus 1, and here y is 1. So these two cancels and we get c is equal to 1. So when substituting c is equal to 1 in this equation, we get this. Here you can substitute v is equal to y prime, and then this is again a separable ODE with dependent variable y. On solving this first order ODE, we get the solution to be y e raised to y minus e raised to y is equal to x plus c1. On substituting the initial value y0 is equal to 1 here, we get that c1 is equal to 0, because we substitute 0 here, 1 here, so e raised to 1, 1 here, e raised to 1, and here y is equal to 1. So e minus e is 0, and this is 0, so c1 is 0. On substituting c1 equal to 0 in this equation, we get bracket y minus 1 bracket close e raised to y is equal to x as a solution of this initial value problem. Here are two more review questions. If the Wronskian is given to be w y1 comma y2 of x is equal to x square e raised to x greater than 0, and y1x is equal to x, then y2 is dash. You can pause the video and try to solve this question. It can be solved by many methods. One is you can use reduction of order and Abel's formula. There is also a direct way of getting a first order differential equation from this Wronskian by taking x1 to be equal to x in the determinant form of Wronskian, and finally you get the solution to be x e raised to x. Next is solve using the method of variation of parameters. The question is bracket x square plus 1 bracket close bracket y double prime minus 2y plus 1 bracket close is equal to e raised to x. The initial condition is y at 0 is equal to y prime at 0 is equal to 1. You can solve this problem yourself. It's very standard. Now we learn another method of solving by undetermined coefficient. This is called the method of solving by annihilator operator. So if A is a linear differential operator with constant coefficient and fx is sufficiently smooth differentiable function such that A applied to fx is equal to 0, then A is said to be the annihilator of the function fx. So what is meant by linear differential operator? So A may be of the form d raised to 4 or d raised to 4 plus d. So A is a polynomial in D with constant coefficients. So here, for example, D4 is acting as A and highlights this polynomial, because D4 applied to this polynomial gives you 0. In other words, you can also see that this particular polynomial is a solution of the differential equation d raised to 4 y is equal to 0. Recall that d is d by dx. Similarly, d plus 3 annihilates e raised to minus 3x. You can easily check that, because d applied to this will give us minus 3 e raised to minus 3x, and 3 when multiplied to this gives 3 times e raised to minus 3x. So the two terms cancel and we get 0. Similarly, d minus 2 whole square annihilates this particular term. Also, you can easily check that d square plus 16 annihilates cos 4x, sin 4x, or any linear combination of cos 4x and sin 4x. You can easily see that, because once we apply d square to it, we'll get back 16 cos 4x with a minus sign, and here we multiply 16 with cos 4x, so the two terms will cancel. Similarly, d square plus 2d plus 5 annihilates 5 e raised to minus x cos 2x minus 9 e raised to minus 6 sin 2x. You can verify that. D raised to n annihilates 1 comma x square dot 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 xn minus 1. It annihilates all of them, but it does not annihilate x raised to n. D minus alpha whole raised to power n annihilates e raised to alpha x e raised to alpha x, and so on, x raised to n minus 1 e raised to alpha x. You can easily verify all this. And finally, d square minus 2 alpha d plus bracket alpha square plus beta square bracket close, and this whole thing raised to power n annihilates e raised to alpha x cos beta x e raised to alpha x cos beta x, and so on, x n raised to n minus 1 e alpha x cos beta x, e raised to alpha x sin beta x, comma x e raised to alpha x sin beta x, comma dot 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 x n minus 1 e raised to alpha x sin beta x. You can easily see that this is the case, that these analytes, so you have to write down and see that this operator, when applied to any of this function, gives the value 0. So here is several examples of annihilators. Now we proceed on to the method of solving using undetermined coefficient by annihilator method. Find a particular solution of fourth derivative of y minus 16y is equal to x raised to 4 plus x plus 1. Here the differential operator here is L is equal to d raised to 4 minus 16. And we have to find an annihilator for this Rx. For this Rx, the annihilator is d raised to 5. So this differential equation can be written as Ly is equal to Rx. This is another way of writing this differential equation. So a solution of this differential equation is also going to be a solution of AL y equal to 0. Annihilator, then the differential operator, then y is equal to 0. You can clearly check that that should be the case, because this is Ly Rx. You apply A on this, there will be ALy is equal to A of Rx, but A of Rx is 0. So you get this. Now this combined ALy equal to 0, this has a characteristic equation, namely m raised to 5 bracket m raised to 4 minus 16 bracket close, which can be factorized as m raised to 5 times bracket m minus 2 bracket close bracket start m plus 2 bracket close bracket start m square plus 4 bracket close. So once you factorize like this, then the general solution of this homogeneous equation, namely ALY equal to 0. This is a homogeneous equation because here Rx is 0 when ALY. So Ly is equal to Rx is not homogeneous, but ALY is homogeneous. Note that this is different from Ly equal to 0. ALY equal to 0 is a new homogeneous equation, and the general solution for that can be obtained by looking at the roots of the characteristic equation. And the general solution is for ALY equal to 0 is C1 plus C2x plus C3x square plus C4x cube plus C5 x raised to 4 plus C6 e raised to 2x plus C7 e raised to minus 2x plus C8 cos 2x plus C9 sin 2x. So here, obviously, because m raised to 5 term appear in the characteristic equation, it corresponds to 0 being a root of the characteristic equation. So that gives us that e raised to 0x should be multiplied with a polynomial of degree 4. So this is a degree 4 polynomial multiplied to ex e raised to 0x, and then m minus 2 term suggests that we should have a term c6 e raised to 2x, m plus 2 suggests we should have c7 e raised to minus 2x, and this last term suggests that we should have c8 cos 2x plus c9 sin 2x. So this is the general solution of the ALY equal to 0. Now in the annihilator method, what we do is we remove from this the part which is also a solution of Ly equal to 0. I repeat, we remove from this solution of ALY equal to 0 the part which is also a solution of Ly equal to 0. So we have to remove this part because this is also a solution of Ly equal to 0. The blue part is also a solution of Ly equal to 0. We remove that, and this is the part written in black, that is the part which remains. So that is the candidate for particular solution suggested by Annihilator method. So we substitute in the differential equation. This is the given differential equation, right? This is the given differential equation. Ly is equal to Rx, that is this. In this we substitute that Yp, the candidate solution, that is this black part, we substitute as a candidate for particular solution in this differential equation. So this is, on substituting we get this. So we simplify. So d4 acting on this, only the last term survives, and there we get 24 c5, and then 16 multiplied to this is this term. Now you compare the coefficients and we get the values of c1, c2, c3, c4 and c5. So c5 is minus 16, c4 is 0, c3 is 0, c2 is minus 16, c1 is minus 5 by 2. So that gives us a particular solution by Annihilator method of the non-homogeneous differential equation that is given to us. So this has to be substituted in this, which gives us the particular solution. Next we solve the differential equation. Ly is equal to bracket d square minus 5d plus 6 bracket close. This applied to y is equal to x e raised to x. The characteristic polynomial of the associated homogeneous equation is m square minus 5x plus 16, which can be factorized as m minus 2 bracket, then multiplied to bracket starts m minus 3 bracket close. So a basis for kernel L is e raised to 2x and e raised to 3x, and the annihilator suggested by the Rx is d minus 1 whole square. This will annihilate the Rx. So we note that we remove the solution of Ly equal to 0 from the solution of Aly equal to 0, and that gives us the yp to be equal to a e raised to x plus bx e raised to x, or you can use the method that was previously told to in that scheme of undetermined coefficient without using Annihilator method. Then from this it comes out that the particular solution will be some qx e raised to x, where qx should be polynomial of degree 1. So here a degree 1 polynomial, namely a plus bx, has been multiplied to e raised to x, and we have to determine a and b by substituting in the given non-homogeneous differential equation. Note that not only that a e raised to x plus bx e raised to x is a solution for this differential equation, even a e raised to x plus bx e raised to x plus c e raised to 2x plus d e raised to 3x is also a solution of the non-homogeneous ODE. But then the second part of this, namely c e raised to 2x plus d e raised to 3x, is also a solution of the homogeneous ODE. So we remove this part to get the particular solution. So that is why we do this procedure of removing the solution of the homogeneous ODE from the solution of ALY equal to 0 in the Annihilator method. So when we substitute a e raised to x plus bx e raised to x in the equation Ly is equal to Rx, we get this equation, namely bracket 2a minus 3b bracket close e raised to x plus 2b x e raised to x is equal to x ex, and comparing the coefficient we can determine what is the value of a and b, substituting it back in this expression of yp, substituting the a and value back in the expression of yp, we get yp or y is equal to 3 by 4 e raised to x plus half x e raised to x as a particular solution for this differential equation. The next example is to find the candidate solution of fourth derivative of y plus 2 y double prime plus y is equal to 3 sin x minus 5 cos x. We will use the Annihilator method in this case. The auxiliary equation here is m raised to 4 plus 2m square plus 1 equal to 0. That can be factorized as m square plus 1 whole square equal to 0. Here the basis of the kernel L is cos x comma sin x comma x cos x x sin x. We have already observed this previously, and the annihilator of the Rx here is d square plus 1. So the general solution of ALY equal to 0, that is bracket d plus 1 bracket close cube of it applied to y is equal to 0. Its general solution is a cos x plus b sin x plus x times c cos x d sin x bracket close plus x square bracket e cos x plus f sin x bracket close. And from that we remove the part which is a solution of the homogeneous ODE Ly equal to 0. So this first 4 terms, the solution of Ly equal to 0, we remove this. So only the last part remains is the candidate for particular solution of the non-homogeneous ODE. So the candidate particular solution is y is equal to x square bracket e cos x plus f sin x. Here is an exercise. Get the candidate solutions by Annihilator method of these two equations.